Section 5.5 is about integration by substitution. I'm mainly just going to do some examples. The main idea behind integration by substitution, sometimes called U substitution, is that we're trying to undo the chain rule. So if you have an integral that looks something like this, you can see that this resulted from the chain rule, and so we want to figure out what the function f and g of x were. Okay, so this is our main goal. Okay, and here's an example. And here's an example where we can actually see the outside, the inside function here looks like this function, so that looks like our inside function. And then over here we see we're multiplying by the derivative of this function. So here we have the inside function's derivative. And to make this look a little less complicated, what we can do is we can say, okay, well, I'm going to take the inside function and I'm going to call that u, and I'm going to say u is x to the 7th plus 5x. So du dx, the derivative with respect to x, okay, and what I'm going to do here is I'm going to write the differential for u, and then I'm going to use that to rewrite the integral as root u times du. So there's my substitution, and that substitution made this much easier to look at, and also it makes it a lot easier for me to see what I need to do to integrate. So I rewrite it, and then I know that this is u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3, plus c. But now I need to go back and write the original u in there. So it's x to the 7th plus 5x. So I'm undoing my substitution. And this is my final answer. This is an indefinite integral, so we were just looking for the antiderivative here. So again, with integration by substitution, usually we're looking for a composition structure, and we're looking for the inside function and its derivative. We don't always see the derivative, but that's the basic idea. It's to undo the chain rule. And we can also check our answer here, right? Just take the derivative and you'll see that the result will be this guy. So let me just check really quickly. By taking the derivative. So I get 3/2. I do the outside of the chain rule. And I get x to the 7th plus 5x, because the 3/2 cancels with the 2/3 to the 1/2. And I'm applying the chain rule. And this indeed is the same as the original integral over here. Okay. So let me do another example. So in this case, I see a composition, and I see this is the inside function, the exponential is the outside. I don't see the derivative of the inside function, but that's okay. In certain cases that happens. So I'm going to let u be negative 3x, and du is negative 3 dx. So I don't see the negative 3 here. So if I want to rewrite this and do the substitution, I have something for dx, and I can rewrite this as e to the u. So what I'm going to do is I'm going to divide both sides by -3. And then I'm going to rewrite this using the substitution. So this is e to the u, and the dx is equal to -1/3 du. So this is equal to, this integral is equal to -1/3 integral of e to the u du. And this is equal to -1/3 e to the u plus c, which, substituting u back, I get -1/3 e to the -3x plus c. Okay, now this is my antiderivative, and you can take the derivative of this function to verify. But the point of this example is that you can't always see the derivative of the inside function, which in this case was -3. And as long as it's a constant, it's not going to be a problem because you can always solve for dx and bring the constant to the other side like this. Okay, so let's do another example. Okay, so in this example, I want to find the indefinite integral. My first guess is to say that x to the 6th is my inside function, but the derivative of this is 6x to the 5th, which is not this function. So then I take the whole denominator and I get the same problem. So this is a special function. This is the derivative of a special function, and that is the arctangent. So I'm just going to rewrite this to help you, maybe you'll see the structure here. Okay, now if I write it like this, it looks a little more like derivative of arctangent or arcsine. So what I'm going to do is I'm going to let u be equal to x cubed, and then du is 3x squared dx, and then I see that right here. Okay, because this I can rewrite this as 1 over 1 plus x cubed squared times 3x squared times dx. Now I'm going to substitute all the pieces. This is 1 over 1 plus u squared times, and this is du. Okay, and then we see this is just arctangent of u, which just gives me, if I undo the substitution, and so this is my final family of antiderivatives. Okay. And you can check that by differentiation, right? So if I were to differentiate this guy, I would get 1 over 1 plus x cubed squared. So using the chain rule, and that does check out to be equal to our original function. Okay. I just wanted to talk a little bit about substitution and definite integrals. So here's an example. Okay, I want to find the definite integral now. So notice how now, unlike the previous examples, I have bounds of integration here. So this is when we call it a definite integral. And that means that we should get a number for our answer. So how do we integrate this? This is not the derivative of any of the trig functions. So I'm going to use a trig identity to rewrite this. And cotangent is actually cosine x over sine x. Okay, so I'm rewriting it like this. Now, why would I do that? Well, I know that this is the derivative of sine and that negative sine is the derivative of cosine. So I'm going to work with that I have a function and its derivative. And in this case, I'm just going to try one out. I'm going to let u be equal to sine x. Du is cosine x dx, which I see right up here. Because remember, this guy is just equal to 1 over sine x times cosine x dx, right? You can always rewrite your fractions this way. Okay, so I go over here, and I'm going to rewrite this. So this is, I'm rewriting in terms of u, so this is du. Now, I'm not going to just write the bounds of integration. This is where I have to be a little bit careful, because once I change the variable from x to u, I also changed the bounds of integration. So as x moves from pi over 6 to pi over 2, what is going on with u? Right? So we can think about this as like having a function where on one axis I have x, on the other axis I have u. And I want to know, as x goes from pi over 6 to pi over 2, what's happening with my u? What is u doing? Okay, so when x is pi over 6, well, sine of pi over 6 is sine of 30 degrees, so that's 1/2. Sorry, that should be down here. Sine of pi over 2 is 1. So what I did was I changed my bounds of integration, like so. And now I'm going to go through and do my definite integral with these new bounds. So the integral of, or the antiderivative of ln u is, of 1 over u is ln of the absolute value of u. Since this is a definite integral, I'm not going to bother adding the c, and I'm just going to evaluate here. So I get ln of 1 minus ln of 1/2. This we know is just 0. Negative ln of 1/2. We can take this as negative ln of 1 minus ln of 2. And my final answer is going to be, this is just 0. So it's going to be simply ln2. That's my whole answer. So notice how in this case it's a definite integral. So I get a numerical answer, not a function. And the key here is that when I switched, when I rewrote my integral in terms of u, I also changed the bounds of integration. You don't have to do that. If you want, you can do exactly what we did in the previous example. Find the antiderivative and then evaluate it at these bounds. Okay? Okay, let me do another example here if you're still watching. This is another example of a definite integral. Okay, and in this case, the main example is I just, again, want to do an example where I have bounds of integration, so you can see what I do differently. I also want to do this example because I want to show you how rewriting integrals can help you to evaluate them. So I've rewritten this as in just a slightly different fractional form. When I write it like this, it's a lot easier for me to see that this is my inside function and this is the derivative. So I'm going to go ahead and use that in my substitution. So u is 1 over x. That means, which is x to the negative 1, du is negative x to the negative 2 dx. So basically, I see that right here. So it's like I'm translating into a different language. This becomes e to the u. 1 over x squared dx, well, that's negative du. So I'm going to put the du here and the negative here. The bounds, now remember, I could go through the whole process and find the antiderivative in terms of x and then plug in 2 and 1. Or I could just change things at this point. It's much easier for me to just say, okay, well, if x was 2, then u is 1/2. And if x is 1, then u is going to be 1 over 1. So that's just 1. Now I'm going to just evaluate this definite integral. This is going to be negative e to the u, and I'm going to evaluate from 1/2 to 1. So let's see, we get negative e to the 1/2 minus negative e to the 1. And I can rewrite this as e minus e to the 1/2, which is just root e. So this is my final answer. Again, notice how it's a number. It's numerical because this is a definite integral.